Welcome to another podcast. In this episode, we're going to be looking at margin of error statistics and also confidence intervals. Sometimes the margin of error statistic that we calculate is called the sampling error as well. And it all really revolves around this formula, which I'll do my best to explain. And so I'll call this the standard error formula, is given by, so bear with me a little bit on the notation here until I explain what it is. You should understand 2 out of 3 of these. So the first part of this is the Z alpha over 2, which I'll talk about here in a second. But then we know sigma is just simply the population standard deviation, and n is the number of data points. To show you what Z alpha of 2 is, I'd like to draw a picture of it first. That's probably the easiest way to understand it. So let me draw a distribution. So we've got a bell curve. And we know at the center of the distribution is the mean. Now, the whole idea behind statistics is generally we do not know the population mean. And we create a sample in order to gain some insight into what that mean is. And this is where sampling comes in. You sample people that are representative of the population in hopes that the value you get for X bar, or the sample mean, reflects the population mean or is close to the population mean. This value, Z alpha over 2, is a point on this curve such that above this point and below this point is alpha over 2% of the data. If you add up those, that's a total of alpha, which means inside here is 1 minus alpha. Now, what is this alpha business? Well, alpha is typically called the confidence, or the confidence statistic. For example, if alpha was 0.05, then this is a 95% confidence level. So alpha is your confidence level. Now, why is that? Well, because if I let alpha be 0.05, then half of 0.05 is 2.5% here, 2.5% here, leaving 95% in the middle. And so this Z alpha over 2 is usually called the critical value. But all it is it's the data point such that 1 minus alpha, or your confidence amount, which is 95% in this case, is in between those two values. And so what this problem really comes down to is figuring out what Z alpha over 2 is. So in the example we're going to do below, I want a 95% confidence level. So let me go ahead and find out what the critical value is at 95% confidence. Alpha is 0.05. So all I'm asking you to find is the Z value, or the value here that corresponds to 2.5% of the data is above it, or 97.5% is below it. Well, here's how we would do this in class. This Z.025 is simply just the inverse normal. We'd use our calculators to find this. It's the inverse normal of 0.975 is the percentile on the standard scale 0, 1. So if you have your calculators handy, you want to go ahead and get those out. And we'll go ahead and calculate so we'll go ahead and find our inverse normal command right here, and we'll calculate it on the standard normal scale at the 97.5 percentile. So according to the calculator, this is approximately 1.96. Alright, so at least at the alpha 0.05 level, or the 95% level, I can replace this Z alpha over 2 with 1.96. Now next up is, what do I do with sigma? Because sigma is the population standard deviation. Typically we do not know that value. Well, it turns out that there's a really nice, simple formula to calculate sigma if what's being reported is a proportion or a percentage. In that case, sigma can be defined as P times Q, where P is the number of yes and Q is the number of no. And here's what I mean by that. If you're calculating a statistic and 58% of people said yes, then that means 42% would say no. And we're going to look at this in the example below. So just hold on in regards to that. But because this is a square root and this is a square root, typically you see this written like this. Now that all seems pretty complicated. I will say this, that regardless of what P and Q are, the biggest that this number can ever be is 1/2. And so oftentimes what you see textbooks do is they'll take and they'll replace the 1.96 with 2 because they're estimating. So let me just say that this is approximate. And they'll replace the P and Q with 1/2, and then they still keep the square root of n on the bottom. Well, 2 times 1/2 is 1, and so a lot of times in textbooks you'll see them tell you that the margin of error is approximately 1 over the square root of n, and that is a 95% confidence that you're trying to calculate if you use that statistic. We want to be able to calculate more than just 95% confidence intervals. We'd like to be able to do 90%, 85%, 99%. And so we're going to be using this full formula, but for this example I'm going to showcase it at the 95% level. So let's look at the example we have down below. And what I want is I want a 95% confidence interval about the statistic. Now understand that when I say I want a confidence interval, all I'm asking for is this interval right here. This is the 95% confidence interval. I just have to figure out what these values are for this problem. So looking at this example, we know our n is 280. We know that our proportion P is 58%, which means that our proportion against Q is 42%. I can use these to figure out or estimate the standard deviation of the population, 0.58 times 0.42. And it turns out that that total is 0.494. All right, the next piece to our puzzle is what is square root of n? Square root of n is the square root of 280, which in this case, let's bring our calculator back, square root of 280 is 16.73. All right, and then what's the last piece we need? Well, since I'm dealing with the 95% confidence interval, we already calculated it above. Z alpha over 2, Z alpha 2 is 1.96. So let's put this all together to get the standard error. The standard error would be 1.96 times the 0.494 divided by 16.73. So let's once again calculate this. .05, we'll call it 0.058. Now, this is as a decimal. In terms of this problem, since we're quoted a percentage, this is really 5.8%. So this is the error. This represents 5.8% this way, 5.8% that way. So realistically, what's happening here is the following. We have our distribution, and for this particular problem, we know that the median is 0.58, or excuse me, the mean, and the median, 0.58, 58%, and I can go up or down based on this to get my 95% confidence interval. And so if I take the 0.58 and I add 0.058, I'm at 0.638. And if I do the same thing but subtract the 0.58, I'll get 0.522. And all we've managed to do is find two values on this scale such that 95% of the data is in here. Here's what this means. It means that this 0.58, even though it might not be correct, I'm 95% sure that the real value is somewhere between these outer 2 points. So we say in that case that our 95% confidence interval for this set is that the actual percentage, and when I say actual percentage, I mean if somehow we were able to sample every single college freshman there is, that would be our population, then the actual answer we could expect is somewhere between 52.2 and 63.8%. Now, that's a pretty wide margin, and when you start thinking about polling this time of year with elections, typically they don't look at 280. The typical sampling size is 1,000 or even 1,500. And the reason for that is they want their confidence intervals to be much smaller. So a lot of times you'll look at a poll, and at the bottom of the poll it'll say something like, you know, you might have Obama and Romney. And, you know, it might be some kind of poll where they've got 48% one way, 52% the other way. And they might say at the bottom of the poll, this is done plus or minus 3%. Well, that plus or minus 3% is the margin of error for the poll, and it's calculated very similarly to what I've done here. But please understand that that plus or minus 3% means it's very difficult at that point to tell who's ahead, because if you add 3 to Obama's, you get 51, and if you subtract 3 from Romney's, you get 49. And those, because the confidence intervals would overlap for a poll like that, it's really hard to tell who's ahead in that case. And so this is a widely used statistic, margin of error. It's only appropriate if your data is normally distributed. So let's make sure that we understand that everything I've done here is only usable if the data set in question is a normally distributed data set. But this is sort of the basics behind margin of error. And if your book or whatever you're reading quotes you 1 over the square root of n as the margin of error statistic, I hope you'll have a little better understanding of where that comes from. We're going to be using the critical value formula in class, and so you'll want to get a little bit of practice with this. All right. Thank you for watching.